Okay, students, a bit of MATLAB then to round out this week of the lecture for some stuff that will carry us forward through the whole quarter. So what I do, I have is some MATLAB code sort of running in here, and this is just the code that I wrote to analyze some cratering data I took a while back. It's not nearly as complete as the experiment you did, but you see I just sort of have my data points in here in arrays. I have my uncertainties in here, and I do some things, I convert to meters and no big deal, and just sort of keep going. Many of you did the same thing. Here's where I go into log space, calculate the energy, and here's that funny error analysis bit that I just showed you in Taylor about how you transform data through the log, the uncertainty through the log. And now what I'm doing here to do the fit, as many of you did, I'm using this function called polyfit here, which is very nice. It does a polyfit, and I just pass it the two arrays. There's my x-axis value and my y-axis value. So E log is my log of energy array, and D log is my log of the diameter array. Those go on the x and y axes, and I tell polyfit to give me a fit of order 1. That's a line. Then I can actually extract the fitting parameters, f sub 1 and f sub 2. And so if I run this here, it's what you'd sort of expect. Here's the plot I get. You see the nice curve fit. Axes labels are titled. You see my data points as individual symbols there. You see the error bar. So everything looks very nice. And of course, if I want to extract the fit parameters, which I can just go over to the command window right here, and I can see that the fit parameters for f, the slope is right here, 0.24, so I'm right on with the 0.25 we expect for the craters, and there's the y-intercept right there. And so this is very nice, but the only problem with polyfit is that this is sort of the result that I'm going for, but it never tells me the uncertainty in the slope. So it tells me the slope of 0.24, but plus or minus what? Remember, we have to report the uncertainty in this case here. So how are you going to do that? Well, the way we're going to do it in this class is you just sort of have to not use polyfit anymore, because polyfit doesn't give you the uncertainty. So what we're going to do instead, let's just sort of comment this out, because we just can't use it anymore for that reason. It's quick and easy, but doesn't give us the uncertainty in the fit. We're going to use this other MATLAB function called fit, and you have to install the curve fitting toolbox to do that. And it's all free, of course, if you're a Cal Poly student and stuff. I can give you some hints how if you haven't done that. But in either case, it more or less works the same way. I tell it to pass in E natural log and D natural log. Those are the same arrays as above, but I've got to transform them using the quote there as column arrays there. And then I just sort of give it in a string the function I want to fit, mx plus b, right? And so if I sort of run this now, okay, there it runs. Now I don't quite have the fit turned on, so well, actually I don't need to show you the plot at all then, but let me go back to the command window. If it runs now, you see some different things going on here. This is sort of the output of fit that I called, if you recall in my code here, I'm assigning it to variable f right there, as you can see. And if I go back to the command window, here is the output of f. And so what you see, it gives me these things called the coefficients with 95% confidence bounds. And so see, it's telling me, it's telling me, say, for example, what my slope is, 0.24, about the same as the other one. But now it's telling me the confidence bounds that it sort of agrees with internally itself. So it tells me that your result is 0.24, and we're pretty sure that it's confident between 0.7 and 0.4. So quite a range in there. But see, it's given me sort of the maximum minimum that it's confident with within 95%. All right. So let's just see what all this means here. If I go back, then basically just a couple of things. I can extract the fit parameters into this function called dfit here using sort of this object notation. It'll be f dot m plus f dot b. So basically the slope times the energy array plus the y-intercept in there. Okay, so you sort of have that going. And if I go back to the command window, you can see that when b and m are in this function f, you can retrieve them using that dot notation. F dot b gives this and f dot m gives that. So of course, if I just run this, then I get about the same plot I showed you before. I have my fit in there now, but it's done using the fit parameter. But here's the compelling reason to use fit and not polyfit, because it is returning this confidence interval here. Now, we don't like the 95% confidence range because that not consistent with our idea of these random errors and normally distributed random errors within the 68%. We normally like to think of confidence as being more tied to that normal distribution of 1 sigma on either side of the average, so 68%. But never fear, what you do in that case here is basically you run f, which remember is the return of the fit function, through this function called compint, like confidence interval is what it's short for, and I'm telling it to rescale the answers to the 68% level, not the 95. So f1 then would become my new fit variable that I can use, but it's not, I'll just leave it at the moment here, but let me run it and just show you what happens here. So if I run it, no major changes up here. The fit is the same. But if I go back to that window, the command window right here, you can see what it's done now. F1 has been dumped out of the compint function, and you can see now that it's given me, it's a little bit different the way it's formatted here. The 1.47, this parameter here, the 1.4771 and the 1.7269, that's now its confidence interval in the y-intercept. You can see how they changed. The 1.2 has gone to 1.4, 1.9 has gone to 1.7, so it's much tighter than it was before. Likewise, you can see the same thing in the slope now. The slope is still 0.24, but instead of this thing being certain about that between 0.07 and 0.4, which is quite a wide range, in the 68% level, it's now bound to 0.17 and 0.31. So how does that help me with my uncertainty? Well, what it's telling me is that the slope of that line, according to fit, is 0.24. And it can be as low as 0.17 and as high as 0.31. And so really what you would do in the command window, you'd say, okay, well, what's the largest range here? Is it 0.31 minus 0.24? That gives a range of 0.07. Or is it 0.24 minus 0.17, 0.24 minus 0.17, which is it going to be? That's, well, 0.07 also. Okay, so basically the upper and lower bounds of MATLAB's confidence in the fit parameter, these two variables, this one and this one, are each about 0.07 from the slope. So that would be my uncertainty. So I can conclude then from the fit function that my slope of this line is 0.24, 26 or whatever, how many sig figs you want to reach, 0.24 plus or minus 0.07. That's going to be my answer. So that's why we should really use fit for the rest of the quarter, because it gives us the 95% confidence interval raw, but we can rescale that using this comp in function here and get a confidence interval that's more consistent with the normal distribution and 1 sigma that we're used to dealing with. And we can now get the uncertainty in the fit parameter, which is critically important, because you've got to ask yourself, where else are you going to get that uncertainty if you don't get it from the fitting function itself? Okay, so just a bit of a MATLAB tip for you right there. Please get yourself in the habit of using this pair of lines right here. Do your fitting with the FIT function fit. Remember, column arrays, not rows. And then rescale the result with this comp in function to 68%, and you'll be all set to get your uncertainty consistent with the ideas of random errors.